Hello, my name is Robert Pittman. I'm an electrical engineer from Sacramento. The next topic that I wanted to talk about is what an MPPT tracker is. So I mentioned it just a few minutes ago. I showed you how PV Rocket drew that one line diagram for us and how it showed the strings going into the inverter, and then there was 3 separate inputs into the inverter, and I said that those were the trackers. So what are trackers? So it's maximum power point tracker. So if I create a chart that shows the short circuit current, which I said was 6.7 amps, I believe. Short circuit, and then the open circuit voltage is 45 volts. So when there's 0 volts, because it's short circuited, you got 6.7 amps. When there's 0 current, because it's open circuit, you've got 45 volts. So this is the open circuit voltage and the short circuit current. So the way this works is there's a slope. It's very small. It's almost flat, but there is a slope to it of the short circuit current as you increase the voltage. So you increase the voltage away from 0 volts and you start to get that current. When you get out to open circuit to the 45 volts, there's a definite slope over here. It's much greater. And as these two things come together, there's a nice little curve here. Now remember, watts equals voltamps, especially when you're talking about DC. There is no power factor on DC. Where is the goal is to get the power, the wattage, into the inverter to be converted. So where is the peak volt power? If you graphed power over voltage, it looks something like this, and the peak is right there. Okay, fine. Over here, is the peak here with a high 6.7 amps, or is it over here with a higher voltage and a little bit less current? And there's a tracker that figures this out. So if this value is 36 volts, for instance, and let's say this is 6.4 amps, so the power would be 36 volts times 6.4 is 230 watts. Let's say this one is 40 volts, but the current is down to 6.3 amps. So the wattage, and I hope I took these, I'm making these numbers up on the fly. I hope I did something good here. Actually, it would be less than 6 point, because this was 6.7, this was 6.4. Let's say this is 5.8 amps. So 40 volts times 5.8
is
232. So I didn't do a very good job. Usually the maximum power point is this one up here. But you get the point. The maximum power point tracker is tracking this curve and finding the peak of the wattage versus volts. So it's varying the voltage on this curve and finding where the product is greatest. Watts times volts. Now, it may seem like something that could be field adjusted one time and left. You know, you buy a Trina or a Canadian Solar module, you buy this module versus that module, you install it, you could manually dial this into the peak and walk away. That's not what happens. You can't do that. It's a dynamic changing thing on the fly at all times. And what happens is the modules put out a series of these shapes, and so the peak at 1 second might be 40 volts, but 45 seconds later the peak might be at 29 volts. And remember, it's varying this on a string basis. So what we're really talking about is varying the string from 980 volts to 870 volts. Like that. And because of the way the strings work, the voltage is cumulative off the module, and that's how it works, is by varying the string voltage. So why would it go from 40 volts to 29 volts, and why would it be dynamic and constantly changing back and forth? What are these curves? What is the difference between these? And the biggest difference is irradiance. Let's say a cloud goes by. It changes the incident light energy onto the modules, and these curves change and shift. Let's say it's super bright, not a cloud in the sky, but it's also very stagnant air, and then suddenly a breeze comes up that changes the ambient temperature and cools the modules off a little bit, and that also can change these. So let's look at the cut sheet for Trina that I had up before, and you'll see this on these charts that they give us. IV curves of PV module for the 370 watt version. The short circuit current is 9.8, somewhere up there. The open circuit voltage is about 48 volts or something like that, and you could see that these curves change with the light irradiance, incident light energy. So at the top is the standard test condition of 1,000 watts per square meter. 800 watts per square meter will get you a different output with a peak of about 7.9 amps instead of the 9.8. So you see how all this, the voltage doesn't actually vary very much. The voltage is somewhere through here, but the current output is what rises and falls with the conditions in the field from 1 minute to the next. And that's what a maximum power point tracker is. So why is this important? Let's say you have a house. Oops. Let's go back to this. Let's say you have a house shaped like an L, and you have a ridge down the middle, and you've got 10 modules over here and 8 modules over here, something like that. And we didn't do microinverters, we did a string inverter off to the utility. Let's say we did a string inverter. These, you've got a certain amount of light incident here and you've got a different here because they're faced differently. You could never string these together on the same string. You would not want to do that because the maximum power point tracker could never properly get both of them. I mean, it could optimize the output of the string still, maybe, but they're producing at, because of this chart over here, they're producing at different currents and everything, and it just wouldn't work. So you want to keep your strings on the same plane, the same tilt, the same orientation and everything, so that they can be tracked properly together. And that's what I wanted to talk about, trackers. And before I move on to the next topic, I wanted to mention that there's a few different things that might be happening. So you have the module, and then you have an inverter. Especially on a string inverter, there might be something between here. There's the code calls them DC to DC converters. That might be in here that you might want to do. Sounds a little funny, DC in, DC out. There's a company called SolarEdge that produces these, and they call theirs optimizers. And then there's another thing out there called rapid shutdown devices. Let's talk about rapid shutdown first. So let's say you have a system and a fire breaks out in the building. Oh, I never talked about anti-islanding. I forgot. Let's go back up here. Where's my eyeballs? There's my eyeballs. So I've got the inverters that are watching the grid and are producing voltage to be able to fall onto the grid at 480 volt. So with voltage drop, they rise up. I want to point out here that it's another form of safety factor, that when the grid goes down, there's a power outage, the inverters don't produce anything. And this is called anti-islanding. So creating an island of power that remains on is dangerous. Let's say you had a power outage. This line right here falls. They're going to roll trucks out to fix that. You can't have power. They're expecting it to be dead, and they'll test it to make sure, but you can't have power being produced on your house that is backfeeding onto the grid when the grid is down. It would be creating current and voltage where the utility workers are not expecting any, because they think this side is dead. They think this side still has power, so they want to come up here and grab these and reach it back up, and you can't have power down there. So if you wanted to have backup, you would have to have some way of disconnecting the inverters from the grid, and you could do that with a battery system or a ATS, an automatic transfer switch. But a standard off-the-shelf inverter has no capability of producing a sine wave on its own. It is simply watching the grid and matching it. And that's why you don't have any power, because batteries are expensive. Transfer switches, what we want to do is grid tie straight into the main switchboard and backfeed onto the grid when you're producing more than is required, and that's all there is to it. You don't want to, you're not trying to support anything, and so it's anti-islanding that makes that go down. And the reason I thought about that is I was talking about the rapid shutdown devices. So let's say you got a system up on the roof, there's a fire breaks out, the fire department rolls up, they want to shut the system down, and so they do. They pull the switch and the inverters stop producing and everything seems great. But don't forget that as long as sunlight is hitting the modules, they're producing DC power through the house to the inverter terminals. It's not going past that, but there's still power in the house on the roof. So as the fire department comes in and sprays their water or cuts vents into the roof, the DC still has power, and that's been a problem for decades. And now they have a rapid shutdown requirement. At least they do in California. If you don't have it in your area, it's coming. So the way it works is you put this device in the way between your module and the inverter, and it's watching the inverter just the way that the inverter is watching the grid. So when the grid goes down, there's a power outage down here, the inverter goes down, this sees that happen and it shuts off the power. So the only thing that has any power is this little segment. This little segment here is dead, and this little segment on the back is very short. What you do is you attach these rapid shutdown devices just like a microinverter. I said that they were I said that microinverters were the size of a book and mounted right to the back of the module. Same thing for these rapid shutdown devices. They're very small, right to the back of the module. So basically it stops the power from going through your house or your commercial building. When the fire department wants to shut power off, they can, and it increases the safety immensely. So that's a rapid shutdown device. DC to DC converter is a rapid shutdown well, I have to think of my Venn diagrams. Which is which and always and everything, but these are two sides of the same coin, basically. Rapid shutdown devices and DC to DC converters. Now, SolarEdge creates an optimizer. An optimizer is a DC to DC converter that has a maximum power point tracker built into it. So you get kind of the advantages of a microinverter, which is optimizing module by module, but you don't have the cost by having inverters at the back of every module. You only have a central inverter. So each module gets optimized, and when the inverter goes down, the optimizer shuts down also. So you pick up rapid shutdown capabilities inherently, and you can put if you had a SolarEdge, you could use a SolarEdge string for any facing module at any point in the system, because it's optimized module by module.